Hello, and welcome to diffuseR, bringing Stable Diffusion to R. You might hear some applause there in the background. I thought it would be more fun for me to record this with some sort of audience interaction, and so I've got some sound effects. Stable Diffusion 2.1 and SDXL are implemented now. Trying to model it off of Hugging Face's diffuser's Python library. We'll see how closely I stick to that going forward. I really like functional programming, not hardcore functional programming, but I think in terms of functions as a statistician. And right now it works with x86 CPUs and NVIDIA GPUs. Anybody else wants to submit a pull request for Mac or ARM processors, you let me know. You can do that right here at github.com/cornball.ai/diffuseR. All right, so motivation. You and R can just do things. This is the new mantra of Silicon Valley, is that you can just do things. And one day I thought, yep, I should program some real AI in R. I'd seen a few other people do it, and I thought, oh, image generation would be easy. It wasn't that easy. Our users deserve first-class generative AI, not just wrappers and APIs. I mean, R is a very powerful language. We all know that, and I'm sure you're hearing about that today and yesterday. But you know, there's definitely places for wrappers and APIs, but I think our users deserve better. And we have a lot to bring to the world of AI research and applications. I've got some good stories. You can talk to me at the happy hour afterwards. This is an attempt to make that accessible to the R users. Python is very object-oriented. Again, that's not how my machine learning, data science, AI brain works. I think in terms of functions, and I've just been using R for so long that overly object-oriented, again, tends to be very verbose and read it a little bit slower. Additionally, I'm an Ubuntu user burned by Python dependency hell one too many times. I've heard good things about UV, but for anybody who's forgotten to enable their virtual environment and destroyed their Linux operating system, my heart goes out to you. And local inference is private, cheaper, flexible, and fun. You should, own your large language models and your AI workflows. And this will help you do that. And the goal was for just an MVP of diffusion-based image generation in R, and I think I succeeded in doing that. All right, so architecture at 10,000 feet. Denoising diffusion model. So, you have a bunch of pictures. How they train up the neural networks are they add a little bit of noise to it, and they say, hey, all right, here's this noisy picture. Predict what a clean, nice picture is going to look like. And that little bit of noise is time 1, and they want you to predict time 0, the denoised image. And they do that iteratively with more and more noise. And so when you go to create or generate an image, you start out with all the noise, and you add in your text prompts, and I'll talk about that a little bit later, and you just iteratively subtract the noise according to how your text prompt tells it to, and as it iteratively subtracts that noise, you eventually get a real, clean image. Real. So here is again, the architecture in code at 10,000 feet. You have a prompt, a pirate with a speech bubble saying R. That's the little pictures I've had here. You've got, you take those tokens. So the prompt goes into a tokenizer that gives you discrete tokens. Typically in the clip tokenizer that we use, it's 49,000 tokens if I'm correct. Those tokens get embedded into basically a matrix. I believe it's 77 by 768. You could call it a tensor if you want to add that third dimension, but it's just a single, it's just one-dimensional in that respect. So you could just think of it as a matrix. Then you start out with that noise, so our users would know our norm. So you'd start out with noise. They're called latents because your image space is 1024 by 1024 by 3. So RGB is that third dimension, and 1024 length by width is typically what these pictures come out at. Turns out that is too big of a space. So they sample it down to a latent space. And I believe that's, it's divided by 8. So if it's 1024, it's 128 by 128. And then they add a fourth dimension there. And instead of 3, presumably we pick up some of those interactions. And that turns out to be about 2% of the parameters, if you will, or pixels or voxels or whatever you want to call them, relative to the 1024 by 1024 by 3. So that's why the model works in this latent space. So you get this noise in this latent space, and then you take that noise and the time step. You start out at 1,000, which is max noise, or 999. The R Python plus or minus 1. I'll talk about that a little bit later. And then you add in the text embeddings and throw that into your UNet. That's the most computationally intensive piece that typically goes in your GPU if you have the room for it, and that predicts the noise. And then your scheduler sort of orchestrates all that noise. It takes your existing noisy latent, your time step, the noise prediction, and gives you a new, less noisy latent. And you just do that in a for loop. Typically 30 times is the default that you will do that. And then you take that last denoised noisy latent and put it into your variational autoencoder decoder, and it decodes it back into the RGB 1024 by 1024 by 3 space. And so that's at the 10,000 foot level. Usage for using the diffuseR package, you call the library, torch local no-grad. I don't know why I commented that out. Oh, because I was thinking about putting it into the function, something for me to think about there. But you want to enable, if you're using Torch, you want to enable local no-grad if you're doing inference so that you don't run out of VRAM or memory. You specify your model, so SDXL, and you specify your devices. So the UNet, again, on this 5-year-old laptop, I have 6 gigs of VRAM. That's just enough to fit in the SDXL UNet, and then I'm forced to put everything else on CPU, which is fine. It's not too bad. On this machine, again, 5 years old, let's see, what do we got here? We've got a GeForce GTX 1660 with 6 gigs of RAM, or VRAM. It takes about 10 minutes, so not super quick. I recently purchased a 5060 for my desktop, 5060 Ti with 16 gigs of VRAM. It takes about 30 seconds, so see how much faster these things are running. You set a seed for reproducibility and put it into the model. Victory is no lie, cornball.ai. I want to talk a little bit about my process for digging into the Python code and getting that working. Again, working from Docker. Didn't use positron. I've been using this setup for many years now for working within Python. Sorry, positron folks, but that is what it is. So you can use Docker and Python from Genie. Genie is an old school IDE written in C only, so if you accidentally install something from Python and break your terminal within Ubuntu, you can still use Genie to get to your terminal. Is a thing that happened to me and why I became such a big Genie fan. You can change the key bindings to be almost the same as RStudio's REPL, which is how I work through code. Is that control enter all the time. So I have it set up to run the current line, just like RStudio. RStudio control 1 to the editor. That's I believe it used to be like that, probably like 10 years ago, but they've since changed it, and I just now set my defaults to be that. Control 2 to the terminal. Use those two quite a bit. So what I would do is I'd have a shell script, and I'd run sudo docker run interactively with all my GPUs. Once you get all that Docker NVIDIA fun sorted out, I'd change directory to the app and fire up Python, and then I'd switch to my .py script and start running these things interactively. And this is how I exported the deep learning models into Torch script. This is how I debugged and figured out all these off by one things, is just interactively going through the code. And yeah, it allows me to work almost as quickly as I do in R. So highly recommended. Got to give positron another try, I guess. I don't have to, but I will when I get around to it. Hardware runtime. CPU works, but you got to have patience. You saw how long it took with the GPU. Memory, 68 gigabytes of RAM is required. Runtime depends on your GPU. Again, this 5-year-old 1660 GPU takes 10 minutes. Thank you for your time.